Good day, beautiful people. Today, I woke up with the intention of rage baiting the public. Right. I want to present to you my essay. Why is SWK 122 so easy? First of all, let me distinguish what this video is and what this video isn't. If you think I'm going to be teaching any SWK content whatsoever, you've clicked on the wrong video. All right. I do have a session this weekend. Depends when you're watching it, but if you're watching it on the day that I'm uploading the video, specifically if you're watching it on the 22nd of August, July, 22nd of July, then there is going to be a session the weekend of the 22nd of July. If you are watching it after the 22nd of July, then that explanation video is already up on the YouTube channel. So you can just go and check that for an actual explanation of real subject content that you can actually publicly see. Okay? That's not what this video is going to be about. This video is going to be me trying to demystify this module and make you fear it less, because I am aware that there is nobody who enters SWK 122 as an engineering student at the University of Pretoria that hasn't been told to fear this module. This module and EBN, I know notoriously people just like to place the fear of the Lord into you, right? This module is going to be scary. This module is going to bite you. This module, people feel like, well, the pass rates is this. It's an easy module. Now, let me distinguish some language here. All right. I'm not saying that you're going to pass this module. I'm not saying that you're going to just pitch up, everything's going to enter your head and you're going to leave and then everything makes sense, right? I'm saying it's an easy module. I use the word easy to distinguish it from the word disciplined, right? It is an easy but disciplined module, right? So it is not a difficult module. It's not difficult and disciplined. It is easy but disciplined. What does that mean? If you remember calculus, right? Specifically integration, and they give you something like x to the power of 3, and they ask you to find the integral of this, the area underneath a x to the power of 3 function, right? Or not really the integral, the antiderivative, if I want to be pedantic with my terminology. Okay, so because you've studied and you understand your rules oh so well, you know that in order to be able to find the antiderivative of something like this, you're going to take the pre-existing power, you're going to add 1 to it, and then that'll be your new power that the x will be raised by, and you divide by that same power. So this is a 2-mark question. And then you're going to say x to the power of 4 divided by 4. And then you hand in your paper, you expect your 2 marks, and then you find that the examiner has come across your paper and has only given you a single mark for this. Right now you're mad, right? You take your paper, you go and tell the lecturer, listen, I've done this. How dare you give me a single mark? I know I've done everything correctly. And it turns out that you forgot a very crucial part of what you had been studying all night for, and that was the fact that you forgot to add the C. That was what was remaining for you to get your full 2 marks, right? But you forgot to add the C. Okay, what makes you remember to add the C? Practicing questions, adding the C wrong, and then adding the C when you're on marking yourself. So for me, that is what I see SWK 122 as. It is not a module itself where the concepts at the core are difficult to grasp. It is a module, however, that requires you to be disciplined in the sense that it requires you to put in the work to understand the basic concepts, the basic rules that we're applying, and then you just spam those rules, right? There is a little bit of problem solving involved in it, but it is nothing that is not algorithmic, right? It is nothing that can't be rote learned. You rote learn the basics, you understand those basics, and you apply those basics, and you pass the module. It is that easy. Now it is disciplined. So to be disciplined obviously requires you to know what to study, how to study, and what is the module even about. I'll start with the third point. What is the module even about? SWK 122 is a statics module. Statics is a field in engineering that is all about the study of things that don't move. Right. That's a very crucial part of engineering. Can I take this particular thing and imagine it not moving? And can I give numbers to that? Can I quantify that? And can I ensure that this is not going to move? I'll give you a practical example as to why that's going to be important, right? So let's say you are trying to build a real life body, right? A bridge. And this bridge is supposed to take the people from point A to point B. Right. Now, obviously, because this is a physical structure, it does have a limit on how many people it can obviously take. It also has limits on how many people can be standing at any particular point, right? Depending on obviously how it's basically built. I'm sure you could probably imagine that if you were to sit or rather stand a little bit further away at the furthest point, perhaps from the supports, like you're perhaps to stand right over here, this is probably going to be the worst place where you want the most amount of people to be concentrated, right? Having 3 people standing at this particular point is a bad idea, whereas having 3 people standing towards the left or towards the right would probably be a bit more of a smarter idea. Now, this is your intuition telling you that, but the whole point of the module is for you to be able to now learn how to attach the mathematics to it. But at large, you want to be able to be sure that when 3 people stand at some particular point, or when people pull a particular thing, when someone hits this particular thing, when a particular force is exerted on this, when you are trying to lift up something and maybe it's 10 tons, whatever, when this truck does this, when this car does this, when this does this, when a ladder does this, like, are we sure that this thing is not going to move? How much force must we apply for this thing to not move? How strong might the structure be for this thing to not move? All these types of things are kind of things that are going to tie into statics, because we're trying to quantify exactly what the magnitude of that force is going to basically be to be able to meet certain criteria. And that's really all the module is going to really be expecting you to be able to do. Now they're going to throw random fancy words at you. They'll throw rigid body, they'll throw equilibrium, they'll throw moment, they'll throw this, they'll throw trusses, they'll throw this, they'll throw centroids, they'll throw all these fancy terminologies and stuff. But at the core of it all, we're trying to solve the exact same problem through it all, which is if stand, would fall, if fall, how fix, right? Simple as that, right? So we're going to be trying to do that. Now, I said I'm not going to teach, but I'm just going to explain the couple of core concepts that we need to understand for this particular module, right? We're not going to do any of the fancy, oh, this is the sine rule, this is the cosine rule. I'm not going to go and explain essentially the orders of magnitude, the units of measurement, all those types of things. We're not going to cover any of that. Again, we have a session this weekend. If you're watching off this weekend, there's going to be a video on the channel. All I'm doing right now is I'm just explaining the concept, right? The need for the module and how the module works, and the core concepts we're going to kind of need to be able to obviously make the most out of the module, right? Or make us hate the module less, right? Because we need to understand what the module is first of all about before we can even know what it is that we're going to study and how it is that we're going to study this particular thing. All right, so let's continue. All right, so the first concept I want you guys to understand is the concept of a particle. A particle is an oversimplification of what happens in reality, right? In reality, we have things of various sizes and shapes and weights and mass and whatever, right? Right now in front of me, I have my laptop, right? The laptop has a particular shape. Towards left, I have the microphone. I'm sitting in a building. There's a chair that I'm sitting on, right? I myself take on a particular form in space, right? You have balloons. You have all these different things that take different forms. You have cars, etc., 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 etc. But what we're going to do is we're going to pretend that for our use case right now, this object is just a dot. And we're going to work with this object as merely a dot. So us oversimplifying a somewhat complex thing and saying, yo, let's just make you a dot is what we're going to call a particle. This object has now been reduced to a particle. Now, when is this going to be applicable? This is applicable when the size of the object, for whatever it is that you're trying to do, and the shape that the object basically has is irrelevant. We reduce it as a particle because we don't need to know what its shape is. We don't need to know whatever. We just know that any particular object will always work in this specific manner, right? So, for example, if we're to look at something like a car, All right. And if we're to compare a car to something like a truck, all right, I am not an artist. I fear God has blessed you many ways, but artistry is not one of them. And we were to be told that they all start with the initial velocity of 0 meters per second, and then that the time that they take to travel some particular distance is going to be 10 seconds. And then we're going to say that the acceleration they were moving at was 2 meters per second squared. And they both did 1, 2, 3. And I asked you for the V of this. Does it matter that the truck was red? Does it matter the wheels had some particular form? Does it matter this truck was maybe 5 times the size and the weight of the car? The answer is no. It made no difference. So what we do is we simplify this thing into a model. We create this object and say, look, I know you're this complex thing that exists in space, but what if you weren't? What if you were just a dot? What if you were just a particle? Now I don't have to worry about your shape or every other aspect of you. I just have to worry about that singular quality of yours. The fact that right now you are just going to be a dot. And then for that particular case, I would say that both of their final velocities would be equal to the initial velocities plus the acceleration they're traveling at multiplied by the time. Therefore, their final velocities would be equal to 0 plus the acceleration of 2 multiplied by 10 is going to be equal to 20 meters per second at the end of the day. That is going to be the final velocity that they both hold. You notice that for me to find the final velocity, I had to acknowledge the fact that their final velocity was independent of the shapes that they basically had, right? That had no bearing whatsoever on what the final velocity was going to be. I just knew that the final velocity was going to be 20 meters per second for both of them. And therefore, it makes sense for us to ensure that we can just reduce it for the sake of our own mental health, reduce this entire body as just a single particle. Now, the whole thing that this module leads into is going to be equilibrium. So we'll talk about the concept of particle equilibrium. But before we talk about the concept of particle equilibrium, I'll take a detour to speak about the concept of a vector. Now, understanding this is going to be absolutely paramount for succeeding in this module. If you don't understand what a vector is, you're going to fail. Right, so now that we have gotten the doom out of the way, how do you make sure we don't fail? We understand what a vector is. Okay, so a vector is really just a line that we're going to use in order to represent the anything that might be acting on a particular object or that might be acting in space. Now, I say the anything because whilst your heads are almost probably hardwired to think about vectors as being forces in this context, vectors is literally just anything that has a magnitude and a direction. So whilst forces, yes, play a very big role in this module, we also need to acknowledge other types of vectors, and the two most important types of vectors you're going to deal with in this module is going to be the moment as well as the displacement. Right, so these three are going to be very important vectors that we need to understand in this particular module, and I'll just kind of explain how they all tie in with each other. And yeah, and then hopefully this module will feel a little less scary. Do watch the recording if you're not in the groups. If you're not in the groups, actually join the groups and also watch the recording. All right, so forces, moment, displacement. What do all this mean in the context of vectors? What is a vector? A vector is an arrow, right? At its core, it is really just an arrow. And it's an arrow that we're going to use in order to represent the magnitude, how big some particular thing is, and where that particular thing is going to be acting. So, for example, if I wanted to have an arrow represent the fact that some person walked from left towards the right, I would say that they walked like this. And then someone else also walks from left towards the right, but they walked a bit of a further distance, so I'll make the arrow bigger. Now someone walked even a little bit further, so I'll make obviously a bigger arrow. Right, so all of these obviously represent the exact same direction, but they represent the exact same direction at different sizes, okay? All right, but regardless, it is the exact same direction, all right? Now, what we decide to do is we decide to obviously quantify or give some particular standard for creating it for defining the directions. And this is where the concept of the unit vector comes in. The unit vector is a vector with magnitude of 1. And because we exist in a three-dimensional space, the unit vectors that the unit vector we're going to use, the set of unit vectors we're going to use is going to be unit vectors that are going to be acting in three separate planes: the x-plane, the y-plane, and the z-plane. A combination of all three of those will be our way of being able to present vectors that act on anything in the entire world. X, y, and z, we literally have any particular vector that could be any particular movement or any particular force, any particular rotation, or any particular displacement that could be acting on any particular object, right? We're going to look at the x, the y, and the z. First of all, the XYZ plane. So the XYZ plane is going to be a plane that tells us that, yo, listen, this is a three-dimensional space, and we have things that can move in the X direction, we have things that can move in the Y direction, and we also have things that can move in the Z direction. Now, we can have things that move in either those directions in isolation, but we also have things that can move in a combination of those particular directions, and they might move at different magnitudes in the different directions, right? We need to be able to quantify that. So before we get too large, we simplify the model first and we say, yo, what if we said that something that moves in the direction from the center to in the direction of the x-axis, why don't we start off with initial size of 1? Right, and we'll say this is 1 in the direction of the x-axis. That's what the 1 I hat means, right? Then we're going to say, okay, I'm moving in the direction of the y-axis. So I'll be 1 in the direction of the y-axis. Just like we say x, y, z, we'll say I, j, k, right? And then that's 1 direction of the j-axis, and that'll be another arrow. And then what we're going to do is going to say, okay, what if we have, again, another direction, right? A k direction. There'll be 1 in direction of the k-axis, right? So imagine yourself standing, right? And I want to speak about how much you jumped, right? Upwards, right? Now you're standing in this particular thing over here, right? You don't move towards the left, you don't move towards the right. You are just going to jump directly upwards, right? And you are quite the jumper, and you're able to lift yourself a whole 1 meter in that particular direction. Now, obviously, I want to quantify this displacement that you've just done, right? So I will say that you've obviously moved 1 meter. But this doesn't tell me the whole picture, because you could have moved 1 meter towards the X, towards the Y, towards the Z, or a combination of all three of those. But then I realized, oh, you just jumped directly upwards. So how do I specify this person jumped 1 meter upwards? I will say this person jumped 1 meter upwards. And that is how I would basically say that, right? So I've now quantified your displacement in terms of both the magnitude, how much you jumped, that was a single meter, right? And also the direction, which is in the direction of the j-axis. So we use j as like our scaling factor, because if we use a minimum, if we create j as being a unit vector, a vector the size of 1, then anything that we put in front of that will basically just scale it up. Right? So if j itself just means 1 in the direction of in the direction of the y-axis, then obviously if I have 1, it just means that I jumped up 1 in the direction of the of that particular axis, right? But if I put 2, because j itself has a magnitude of 1, you're saying take j and double it, and that is the direction in j that I'm basically going to be moving, right? And that'll be 2j, and that's basically it. And then we're going to have 3. Right. Again, I'm just moving in a singular direction, so that's perfectly fine. Okay, now you decide to quit your life as a high jumper, and you decide that you want to become a long distance walker, right? So you, for practice, decide to walk from here, and then you're going to find yourself here. So in this particular case, you have not moved in a singular direction. You've moved a little bit in this direction. Watch how I'm going to do it. And you moved a little bit in this direction. But obviously you're not going to move like that. Nobody moves like that, right? You're not going to move all the way in the X direction and then you run all the way back. And then you're going to move all the way in the Y direction and then run all the way back, right? You're not going to go and do da 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 and then run back, because you also need to move da 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 da. No, that's not how it works, right? What would happen in reality is you're going to first of all move in the one direction, which is the X direction, and then you're going to move, right? And then you're going to move in this direction. Now, what does that mean for me, right? This means that if I were to just say, okay, cool, how have you moved overall? Don't tell me yes, a bit in the X, a bit in the Y. Give me a simple straight line, right? What is a straight line vector? What is the displacement that you've actually had, right? The straight line distance would have been this, right? To simplify the story, this is how much you moved. And that really is all. And we're going to call that your displacement, okay? But what if you didn't move in that specific order? What if you decided, I kind of want to move first of all in the Y direction and then I'm going to move in the X direction? I do not know how to make this a. I'm going to delete the entire. Okay, it's fine. It's fine. We'll just have to be meticulous here. All right. Okay. So what if I moved first of all in the Y direction, and upon having moved in the Y direction, I then move in the X direction? Well, I've moved a little bit in the Y and I've moved a little bit in the X, but you'll notice that the straight line from my start to my endpoint is literally the exact same. So regardless of the order in which I added the two vectors that I use to get to some particular point, the resultant vector remains the same. And that concept is going to be quite important for when we're going to actually get to active problem solving. But you understand vectors now, right? You can move in combinations of X and combinations of Y and in combinations of Z, right? It could be just X, it could be just Y, it could be just Z, but it could also be XY, it could be YZ, it could be XZ, it could be XYZ, it could be any combination of all of those, right? So you need to be able to acknowledge that, understand that that is going to be what you can expect, right? And whilst right now we're talking about just movement, this could be applied to forces, this can be applied to moments as well, right? And those are obviously going to be the three core concepts that we need to understand in this particular module. Okay, now we've spoken about forces. No, we haven't. We've spoken about vectors. Now let's speak about forces in the context of vectors. So what is the forces that we can have that's basically going to be in a particle? The important concept over here, the most important word in this module. In fact, let me give it its own page. I think I grossly miscalculated how much space I needed. All right. Equilibrium. All right. So this is the most important word that this module requires. Right. In equilibrium is the quality of an object to stand still, to not move, to not be in motion. We'll say that this thing is going to be in equilibrium. That's the whole idea. That's the whole point of equilibrium, right? Is this thing not moving? Yes, it's not moving. And then what do you say if something's not moving? That thing is going to be in equilibrium. Okay, so how do we ensure that things are going to be at equilibrium? We're going to talk about two types of equilibrium. The first type of equilibrium is going to be particle equilibrium. And the idea behind particle equilibrium is we're going to go back to that dot and we're going to say, yo, dot, don't move. Okay, so we have a dot and we can apply forces to this particular dot. All right, so you decide, okay, take this, and remember this dot could mean anything. This dot could be your friend, Alfred. This dot could be a car. This dot could be a truck. This dot could be a plane. This dot could be a plane. This dot could be anything, right? But we're going to just acknowledge the fact that regardless of whatever it could be, it is just going to be a dot. All right, so what we can have is we can have someone, right, obviously pull on that particular dot, right, headed in that particular direction. Okay, cool. So you basically pull on that particular dot and you are applying a force on that particular dot. Okay, now physics, Newton also wisely said, an object will remain at rest or uniform, how do they go again, or uniform velocity unless it is acted upon by a net force. Okay, now it so happens that there is a net force. What's a net force? A net force is going to be when there is actually going to be a total force that's going to exist on that object that has the magnitude that is not going to be zero. A non-zero force acting on that particular object. And in this particular case, you are pulling that particular object towards the right. There's no gravity stopping you from pulling that particular object. There's no friction stopping you from pulling that particular object. There's no one pulling the objects in the other direction stopping you from pulling that particular object. So according to Newton's first law of motion, you are not meeting this requirement, right? So that's Newton's first law of motion. What does Newton's second law of motion state? It says that an object, oh gosh, when a force is applied to an object, of mass, the object will accelerate. This feels wrong in the direction of the net force. Okay, so I might be spelling accelerate wrong. That is embarrassing. I have fallen off. Okay, but anyway, regardless, when the force is applied to an object of mass, the object will accelerate in the direction of the net force. Okay, so is a net force? Yes. So this object will accelerate in that particular direction. Now that's a problem in statics, because imagine you build a bridge and someone stands and applies a force on the bridge and the planks accelerate in direction of the weight of the person. In other words, weight goes where? Towards the center of the earth. So now the plank's going to be bending towards the center of the earth, or rather moving towards the center of the earth. Not bending, please scratch that. That's another concept entirely. Right. We'll focus first of all on moving towards the center of the earth. Right. So what we need to be able to be sure for an object to be at motion, no, for an object to be at rest, is that all the forces acting on the object must be balanced. Right. So that means that if there is a force pulling this object this way, right? To balance this force out, there must be a force pulling this object this way. So that when you add these two forces up, they add up to zero, right? If you know about the whole head and tail method, right? You can add the forces and move the head of the one force into the tail of the other force, right? So I'll move it so that you start, okay, basically this is the first force. And then if these are the two forces, what I'll basically do is I would literally just take those forces. I have no idea if I can actually physically move that thing. I'm sure there's probably a way that is beyond me. But basically what I can do is I can take that particular thing and physically move this blue thing to start at the red. And if I do that and I find that when I start over here, I do this, right? A resultant vector is the vector that starts from the first vector you added and ends at the final vector you added. And you notice that our resultant stays right here. So the sum of the two vectors is going to be equal to zero. When you can ensure that, that particle is going to be at equilibrium, right? That's very important. So what does that mean for us? This means for us that if I have a particular dot, right, and I go a little bit this way, all right, and I go a little bit this way, and I want to ensure that this object still is going to be at equilibrium, rather. Let me say I add a force a little bit this way, right? So in this particular case, I've added two forces on this particular object. I probably should have figured out a way to move this thing, which is a bit of a pity. Okay, but okay, I can. Okay, so as you can see over here, when I move this thing like this, it looks a bit like this, right? This is the problem if I'm trying to obviously ensure that the object does not move or stays at equilibrium. Because if I do this, the resultant vector does exist, right? And what does resultant and net force mean? The same thing. And what does Newton say? When a net force is applied on an object, the object will accelerate in the direction of the net force. So what we want to be able to do is we need to add a third vector such that mathematically it takes us right back to where we started off. So if we want to be at equilibrium, we need to ensure that however many you moved in the x direction and however many you moved in the y direction is going to be perfectly counted by however many your resultant, not resultant, your third force basically moves to balance all of those other movements that you did. Right. So that actually makes no sense. That made no sense. That made no sense. That made no sense. I was wondering why the math wasn't making sense in my head. All right. So this guy actually moves up. All right. This guy moves towards the right and upwards. This guy moves towards the right and downwards. Right. And then obviously now this guy has to move all the way towards the left to counteract both of the right movements the other guys did. And then also just has to fill up the remaining up movements to balance out the down movement that this guy had basically done, right? This guy had brought us a little bit lower than we should have basically been. And when we add all three of these up, they bring us right back towards the center. And once we can do that right back to the particle, we would say that particle is going to be at equilibrium. Conceptually, very, very easy, but it requires practice. So you need to be disciplined, but the concept is easy. And I'll show you how easy it is in the weekend session. Or the video is already up, depending on when you're watching this video. All right, so we've got that sorted. Now we need to understand moment. And a concept that needs to be explained over there is a rigid body. Okay, I'm not going to go too deeply on the definition of a rigid body here. All I'm just going to say over here is that we worked on things that are just going to be a single particle. But obviously, things aren't going to be a single particle in real life, right? Because you could apply forces, but where you're applying those forces on the object is also going to matter. Okay, so let's say, for example, you've got that plank, right? You know that plank that people basically swim on, jump on, right? Jump on that particular thing. Again, I want you guys to tap in to your childhood intuition, all right? Someone basically gives this particular plank and basically tells you that you're going to be jumping off the, you're going to be jumping, right? Jumping on the plank, right? I'm sure intuitively you understand that in order for you to be able to jump with this particular plank, you want to be here for the plank to not bend at all. And then if you go a little bit here, the plank will bend a little. You go a bit here, the plank will bend a bit more. You go here, I mean, assume that you're applying the exact same force. And if you're going to be over here and applying again the exact same force, the plank is going to obviously bend a lot more, all right? So the bending is what we call a moment. A moment is when a body is going to bend. Now, why do you talk about a rigid body? Because a particle is just a dot. A particle does not occupy any space, right? It is just simplified as a dot. But if I'm looking at some particular object, right? Yes, I could physically translate the object, right? I could physically take any particular object and bring it from point A to point B. But sometimes you'll be applying forces, and those forces might cause things to tip over, might cause things to start to spin. And we need to ask ourselves, okay, depending on where the forces are applied, how much is that particular thing going to spin? Again, I'm gonna ask you to tap into your intuition here. All right. Imagine that you have a door and you are one of two twins. All right. So this is your brother, and this is you. Now assume that you and your brother have the exact, okay, this is perhaps not, this is you, right? Assuming your brother, because you're twins, have the exact same strength, have the exact same da, have the da. Every factor is going to be the same, all right? And this is going to be a door, and this is going to be the hinge of the door. This is the doorknob, and then the door opens this way. All right. Now, you, because you're so clever, want to open the door, and you open the door from here, from right where the door hinges, right? Right over here. And you apply a force, right? And you're applying a force, 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 and the door is not budging, right? You're trying to push the door as much as you can. I keep decapitating you. You're trying to apply the force as much as you can. You're trying to apply the force, and the door is just not budging, right? And then your brother comes along and applies the exact same force that you're applying 5 seconds ago, and all of a sudden the door decides to rotate. Why did the door decide to rotate? The door decides to rotate because you, because you're so smart, were smart enough to push the door exactly where it hinges. And your brother decides to push the door at a certain distance away from where it basically hinges. So when you are pushing something or applying a force at further distances from the point where it hinges or the point around which it rotates, the exact same force could cause a stronger rotation. So you applying a force close to the hinge and your brother applying the exact same force but closer to obviously the furthest point on the door, the furthest that what's the word, perpendicular point away from where the door hinges, right? So this, you can say, is a perpendicular distance. At that furthest perpendicular distance, your brother applies that particular force directly on the door, and you're applying the exact same force. Your brother will create a stronger rotation on the door, and we call that rotation a moment. Now, if we want an object to stay completely still, we don't want the object to just stop itself from moving from point A to point B, right? Yes, we want to stop the object from actually physically moving, right? We want the object to go from one particular point and then obviously travel, okay, and travel to another particular point, right? But even if it stays at the exact same point, we want the object, we want to also stop the object from rotating. And that's the important aspects. Yes, I'm stopping the object from literally moving from one point to another point, but I'm also going to stop the object from rotating. And that is really all this module is about. We're going to be playing around with concepts and learning a whole bunch of new stuff to just answer two questions. The sum of the forces is equal to 0. The sum of the moments are equal to 0. If yes, yay. If no, how do I do so? And we're going to be looking at how we can basically ensure that for a multitude of different things. But at its core, that's really all this module is going to be about, right? And they'll try to scare you. I've heard the rumors. I know it is easy. I am financially incentivized to tell you that it is going to be easy. I am financially incentivized to tell you that I am able to get you to make it easy. But I hope I'll be able to actually prove it in the weekend session. So if you're watching this before the weekend session, join the free group. We'll cover every particular concept and even go a little bit ahead of the class just to show you how easy the module is. And yeah, in so doing, I do hope to demystify a module that has traumatized UP students for years on. Okay, beautiful people. If you have any questions, this is on YouTube. So you can actually ask the questions in the description. No, it's not the description, it's the comment section. You can ask the questions in the comment section. Otherwise, join the free group. When I share free notes, and I share free this, and I share free that, you're there. And when I advertise premium stuff, you're also there. All right, that has been Swift, and I hope you found this video helpful. I hope it has made this module what it is about a little bit easier, all right? In the session, we're going to focus on the remaining two things that I do not touch on, and that is what to study and how to study. And altogether, I do believe that this module is going to be easy. Okay, so it is an easy module. You just know what to study and how to study. Hopefully, you understand what the module is about first. And then, yeah, I just require that you bring discipline and that you put in active practice. But beyond that, it is an easy module. Beautiful people, that has been Swift. And yeah.